Chapter 5, Part A, Angle of Torsion, Sample Problem 2, Separated Parts. As you can see in this figure, if we call this A, B, C, and D, you can see a horizontal shaft AD from A to D, which is attached to a fixed support at D and subjected to two different torsional torque of T with different values. If we do know the section CD in B to D, it just drilled out. We take out the 44 millimeters out of the 60 millimeters. So CD is a hollowed section. So one can say CD is a hollowed section. And again, with knowing the material is a steel with a shearing modulus of 77 gigapascal, we want to know what is the angle of torsion or angle of twist at free end A with respect to D. So we want to know what A, we want to know what is phi A with respect to D. That's phi A minus phi D. And we do know because D is fixed end, it cannot rotate, so that's 0. So phi A with respect to D, it just goes by phi A. And we want to know what is the numeric value for that in degrees. So let's attempt our problem. So if we just take the A, B, we take portion of it out, C and D. A an element of length of x out from AB, which is the free body diagram of that, and there is only a torsion of 2050 Newton meters applied on AB. If we travel from right to left, from free end to fixed end, and we develop the free body diagram, analyze that, and we can develop the moment equation for a part AB, sigma mx for the length of x equal to 0, and summation, and consider the counterclockwise direction as a positive direction. In that sense, TAB, which is counterclockwise angle, torsional torque, minus 250, which is a applied in problem statement, and that's the direction of the torsional torque is clockwise, so that's a negative with respect to our positive direction, and that gives you TAB to 250 Newton meters. If we do the same for free body diagram of the other part, so that's BC, again with a length of x element, and again free body diagram, this time for BC. Do the same process for part BC, including the previous torsion. TBC, again this is torsion of BC, which is counterclockwise, should cancel out the two other torsion which applies on the structure and provided in problem statement. That's a positive counterclockwise direction, likewise previous top part, and that sigma mx should go 0. That gives us a positive TBC counterclockwise minus a 2000 Newton meters from problem statement that applies at B, and minus again clockwise torsional torque of 250 Newton meters, and that gives us a TB torsional torque of part BC is a positive 2250 Newton meters. The next step is, as soon as we know the torsion for parts. This is a 50 millimeter solid cylinder. This is a 30 millimeters solid cylinder. This is a 30 millimeters solid cylinder, hollow cylinder with the C2 and C1 equal to 22 millimeters. If we know the dimensions of cross sections, the next step is calculation of polar moment of inertia, because in phi equation, in calculation of angle of torsion, we need t, which we just had it, we need length, which is provided in problem statement and in the figure as well, and also gj. So far we had calculated torsional torque for free body diagram from the other from different part. And if we just, let me modify that, that's polar moment of inertia. So the other part is the calculation of polar moment of inertia. By doing so, it it just a matter of polar moment of inertia for different sections. So polar moment of inertia J for AB, which is this one, stands for AB. This is BC, and this is C to D. So JAB is pi over 2 C to power of 4, and the radius is 15 millimeters. That gives us this much of J, polar moment of inertia. Likewise for BC, again, that's a solid cylinder with the radius of 30 millimeters, and that gives you this much of J. And for CD, which is a hollowed section with C2 of 30 and C1 of 22, if you subtract that from each other, it gives you 0.904 10 to negative 6 meter to power of 4. If we know T, torsional torque, we do know length, G is provided in, and we just calculate polar moment of inertia. If we just replace the separate part in equation of phi and add them for different section from AB to BC to CD and add them up together, it gives us the angle of torsion for A. Mhm. Let's see how is that. Again, phi A is, because D is fixed, phi A is the total rotation from A to D. Let's put them all together to see how it goes. So again, this is the angle of torsion of phi A, angle of twist or angle of torsion, and that's a just summation of three different part from I to equal to 1 to resummation of Ti, Li, G, the same material, steel. So it just comes out for all of them. We can factor it out, and Ji. So that's Tab times Lb over Jab, Tbc times Lbc over Jbc, and they are adding up with each other. Likewise, torsional torque of CD comes from free body diagram times the length of CD over J of CD. If we just replace the numeric value for that, it gives us phi A is 1 over G77 gigapascal times torsion of AB, which is provided in from free body diagram, times the length of each part, which this is provided to be 4 point meter. This is 0.2 meter, and this is 0.6 meters. J, we calculate the torsion from free body diagram. We calculate polar moment of inertia in previous step for each session, for each section, and just if you replace and add them up together, it gives you, I just go by 1, 2, 3, 4, 5 digits. You can go by less and more and just add them up together. I think two digits is more than enough, but just in case, it gives you a numeric value of phi and this amount 0.04 in radian, and if you just convert that by degrees, it gives you phi a is equal to 2.31 degree. Thank you.